All right, where are we? Oh, goodness. Okay, sorry guys, bit of a delay here while I figure out what I'm doing computer-wise. Hey, there we are. Okay, and okay, here we are. Sorry to keep waiting, guys. Today's lesson should be review from grade 10, but it's all about ionic compounds. So really quickly, atoms don't have a full outer shell, are reactive, or they're unstable to some degree or another. And that shouldn't be new information. Everything but the noble gases can't just be atoms all on their own. But we know that these atoms can form stable ions by gaining or losing electrons. And because they've lost or gained electrons, ions always have a charge because electrons have a negative charge. So if you lose an electron, you're going to end up with a positive charge because now you have more protons than electrons. And if you gain electrons, you're going to end up with a negative charge. So suppose that you have both sodium and chlorine atoms together. Well, we know that sodium is able to give away an electron to form a positively stable positively charged ion. Don't forget, yesterday we talked about electronegativity. So sodium has a low electronegativity. All right? It has very little pull on electrons. Whereas we know chlorine has a high electronegativity. It is very much pulling on electrons. And so the chlorine will receive an electron and it's going to form a negatively charged ion. All right, and remember, by the way, that this takes energy. All right? So it takes energy to make sodium give up an electron, and we get energy when chlorine receives that. That's not really important to what we're talking about today, which is how they come together, but just tying it into what we talked about yesterday. We have to provide that ionization energy to make sodium give up one electron, and then we know that the electron affinity is released when chlorine accepts that electron. Here we go. We have sodium. It has 1 electron in its valence shell. And we have chlorine. It has 7 electrons in its valence shell. Try not to get too excited. This is pretty high tech here. And of course, sodium moves an electron over to chlorine. All right? Once that happens, sodium now has a positive charge, and chlorine now has a negative charge. And opposite charges do what? Of course, they're attracted to one another. All right, so that should very much be review. But you can take a few seconds and draw that out, right? Long story short, sodium and chlorine. Sodium transfers an electron. Now we have positively charged sodium and negatively charged chlorine. Both have full valence shells. Sodium because it's given away the only electron in its valence shell, and chlorine because it's accepted one more electron to give it a full valence shell. And that leads us to sodium chloride, just like that. Again, I'm going to erase that because I had the animation there. Right, and this is an extremely strong bond. We call it an ionic bond. All right, a very, very strong bond. And anything that has an ionic bond, we call an ionic compound. So any positively charged ion, and by the way, we call these cations. And that's probably language you heard in grade 10, maybe even grade 9, but definitely grade 10. But if you didn't, that's okay, because we'll talk about it now. So any positively charged cation can form an ionic compound with any negatively charged ion. And we call these anions. So cations and anions. In general, that means any periodic table on the left, because remember the left is all things with low electronegativity. They're all happy to lose those electrons. They can react to form an ionic compound with any element on the right, because these all have high electronegativities. They're all really trying to get electrons. And to put it in even other words, to put it another way, we normally have metals forming ionic compounds with nonmetals. So in other words, all of these guys, all the metals, will typically form ionic compounds with those guys, the nonmetals. All right. So now that we know how they're formed, two other things to talk about. The first one is, how do we name these? Well, for basic ionic compounds, they're very easy. We named the positive ion, the metal, first. All right. And the negative ion, the nonmetal, the second, but we change its ending to "-ide". So for example, NaCl becomes sodium chloride, right? So the cation comes first, and its name doesn't change. And the anion comes second, but it's with the IDE ending, "-ide". Another example, of course, would be AlCl is just called aluminum chloride. And MgF2, that's right, I know you all got it, is magnesium fluoride, right? Mg is magnesium, F is fluorine, but again, the ending is changed to "-ide, so it's magnesium fluoride. All right, so take a minute, pause this, and fill out the information on the right. Just on the right for now. All right, and we're back. This first one is barium oxide. Again, BaO, barium oxide. This next one here, MgI2, well, it's going to be Mg is magnesium, and I is iodine, but again, we have to change the ending to "-ide, so it'll be iode, "-ide. Kind of a weird one. And KCl is potassium for K. And then Cl is chlorine, so it becomes chloride, just like that. All right, and I don't want you, I'm going to quickly skip by the left side, because I want to show you that going the other way can be a bit challenging. Sodium bromide is NaBr. That's pretty straightforward. Strontium fluoride is SrF2. You get two fluorines there. And cesium fluoride is just CSF. So that brings us to the next thing, which is, how do we know how many of each ion is needed to make an ionic compound? How is it that I can know that strontium fluoride is going to take two fluorines for every one strontium, but that cesium fluoride will just take one? So let's walk through it, shall we? We use something called the crisscross rule. And the example I want to use first is aluminum chloride. So the first step is always just writing out the name with spaces. So aluminum chloride. And then the second step we write the symbols and the charges of the elements. So the symbol for aluminum is Al. The symbol for chloride is Cl. And the charge on aluminum, we have to look at the periodic table, and we see that aluminum is in the third group, so it gets a charge of 3+. And chlorine is in the seventh group. It's in the second to last group, so it just needs 1 electron to get a full shell. So it has a charge of 1-. If, by the way, it's been a long time since you've done this and you forget how to find this, come talk to me, because I can walk you through and give you some hints. And it's really not so hard once you get some practice. Once we know that aluminum has a charge of 3+ and chlorine has a charge of 1-, we write out the symbol again, and we cross the charges over. So that -1 comes down here with Al. We don't worry about the negative or the positive, because these are going to be counting numbers, and the 3 comes down here. And what it tells us is that because of the charges, because Al has a charge that's 3 times bigger than Cl's, because aluminum is more charged than chlorine, we actually need 3 chlorines for every 1 aluminum. So the crisscross rule is just a trick that helps us figure this out. And then lastly, we write it together as AlCl3, just like that. You'll note that I didn't write the 1, all right? We never write a 1, all right? We always assume that it's 1 unless there's a number written there. So aluminum chloride's formula is AlCl3. Let's try another example. Oh. Well, okay. These are letdowns. But here we have aluminum oxide, and we follow the same steps. So in the first step, we write the names, aluminum and oxide. And then in step 2, we write the formulas. So aluminum is here again, Al, and we write its charge, which is 3+. And here we write oxygen, and oxygen's in group 6, which means it needs 2 electrons more, right? If we were to draw a Lewis structure, oxygen has 6 electrons, and to get a full happy outer shell of 8, it needs 2 more, so it's going to take a charge of -2. And then we write the symbols out again, and we just cross the numbers over. And again, remember, I don't put -2 down here because now we're just counting. And there's no such thing as -2 aluminum atoms. What it's telling me is that it's going to take 2 aluminum atoms to counter oxygen's charge. And then we put this 3 down here, and again, what that tells me is it's going to take 3 oxygen atoms to counter the 2 aluminum charges. So again, we just write the symbols and cross the numbers over. And when we do that, we get Al2O3. And that's the formula of aluminum oxide. And we'll do one more example. Magnesium oxide. All right? Magnesium has a charge. Here, I'm just going to do it this way. I'm going to work with you. We're going to do magnesium oxide. So we write magnesium, and we write oxide. And then we check our periodic table, and magnesium is in group 2, right? And that means it has 2 electrons in its outer shell. And that means when it loses those 2 electrons, when they leave, we get Mg with a charge of 2+. So Mg has a charge of 2+. And as we've already covered, oxygen has 6 electrons, so it needs to gain 2 more to have a full shell. And when we do that, we end up with oxygen with a charge of 2-. There we go. And again, we rewrite the symbols, and we crisscross down the numbers. So the 2 from oxygen comes down here next to magnesium, and the 2 from magnesium comes down here next to oxygen. And what we are left with is Mg2O2, which tells us that for every 2 magnesium, we need 2 oxygens. Let me ask you, is there a better way to write that? if it's true that for every 2 magnesiums, we need 2 oxygens, then it's equally true that for every 1 magnesium, we need 1 oxygen. And that brings us to a rule. Always reduce formulae to lowest terms. Oh boy. Right? Lowest terms. All right, and tomorrow we're going to talk about polyatomic ions, which is when we have to use parentheses. So we're not going to talk about that today. This is where I leave off. So today I left you with some just simple examples. They're in the homework that's attached, so you can work on those. And hopefully in working on those, if you have any trouble, you can feel free to come get me and we'll take a look at that together, okay? And then tomorrow, I'm going to be working with you guys one-on-one, and the 4 U's are going to be working from a video. So we'll be in good shape there. All right. Thanks a lot.